Yeah, so my talk today is toward optimizing exabyte Iceberg lakes. So I am Zhen Wang Albert from Tencent. So Tencent is an internet company that located in China that provides online games and other online services like WeChat, videos, etc. to a large consumer basis. So with that, let's get started. As is largely admitted, the Iceberg has become the standard of the table format. And like Ryan has mentioned in his opening, Iceberg provides the basis functionality, this solid basis functionality that we can rely on, so that we can build our functionalities on top at the application layer. So with that, we're now managing like hundreds, thousands of Iceberg tables in the company in production. Most of these tables are V1 append only tables, with a few, some of them are V2 upsert tables. Regarding the share numbers, like 99.9% of them are V1 append only tables at the moment. And the remaining 0.10% are the V2 upsert tables. The numbers are continuing to grow, and we are seeing some surge in the V2 tables recently. So with these many tables, we are handling around the exabyte table storages. And we are dealing with the billions of files generated by these 100,000 Iceberg tables. With these tables, we are processing like 1 million queries daily. So this is our scale. That is a fairly large number. So in order to run this large Iceberg lake, we're facing challenges. So the first challenge is the users. We have very diverse user backgrounds, and we have very diverse user backgrounds and businesses. They come from very different backgrounds. So we have users from a data engineer background. So they have knowledge regarding what is a table format, how to maintain an Iceberg table. So we also have users from, like say, analysts' perspective. So they know how to create a table using the query and how to query the tables. But apart from that, they don't know how to maintain the Iceberg table. We have the users that create tables that commits very frequently, like within minutes, they will commit a couple of times. And also tables that is committed less frequently, like say a couple of commits within days, weeks. Most of these users interact with the Iceberg tables. They just interact with the tables just like the old Hive tables. They know that the Hive tables have certain shortcomings. They want to use the Iceberg tables to overcome those shortcomings. Most of them actually lack the mindset regarding what to optimize for the table. They want to operate in a world that they just create a table and then query the table. They don't know the remaining part. So even for the knowledge user who has a certain understanding in how to maintain the table, they don't necessarily do that. Users anticipate all optimizations happen automatically with no intervention. So that poses a challenge for the platform which we provide. So the second challenge is actually configurations. There are many optimization aspects to config. So like the time to live config for the data. This is actually not new. We have to remove the expired data in a timely manner. Otherwise, when the users receive their storage bill, they will be surprised. And the second is the expiration time for the metadata. So this is new. the metadata holds references to the data files. If the metadata is not removed in a timely manner, the data files will be retained. The third is the rewrite options. It's hard to say that we have a set of fixed options that suits for all table needs, for the large tables, for the extreme large tables, for small tables. We don't have that kind of rewrite options. The fourth is in order to further accelerate the query execution, we usually cluster the data together. So for this to work, we have sort columns, the order columns to config in order to skip more data by clustering the data together. So this is the left-hand side is the configurations we have to come up with, and we have to actually do. The right side is what we actually observe in the production. The users actually don't config, like mentioned previously. They anticipate all optimizations happen automatically with no intervention. Even for the knowledge user like data engineers, they know they have to like tune these configs because they actually manage a lot of Iceberg tables on this platform. Sometimes they forget for those less important tables, forget the tables with low service level agreements. And for most of the users, they don't have those kind of knowledge, so they simply don't know how to do the config. The third challenge is the tables. So, like I said, we have very different backgrounds of businesses, and we manage very big tables. We have single tables with petabytes of storages, and these kind of tables are very sensitive to the storage. If the data is not removed in a timely manner, the storage bill at the end of the month will surprise them. And we also generate a lot of data files with those highly frequently wrote tables, like the V2 tables. We have V2 tables at the scale of tens, hundreds of terabytes. These kind of V2 tables, they can accumulate quite a lot of small files within very short time. So these tables are actually very highly sensitive to the rewrite optimization. So if you don't do the compaction in a timely manner, the query performance can degrade very shortly, like say in hours. So for these tables that with very frequent writes, timely and incremental data rewrites are expected, and plus data rewrites with minimum user config. They don't want to intervene with these optimizations. And the third category of tables are not that important. They are in the number of tens of thousands. They are of low priority, and they have like write patterns a couple of times within a day or even a week. So although these tables are of low priority, they are still expected to be optimized in a timely manner because the sheer number of them are actually very large. So if you add all those tables, the small files, the storages together, because of the sheer number of them are actually very large. So if you add the total number together, there will be still, there will still be a considerable amount. So among solving these challenges, we derived several goals along the way. So we keep these goals in mind, and they guide us toward solving these challenges. The first is lowering the storage cost. We already have have the expiring data files in place with the community version. So so that with that we can expile those expiled metadata in a timely manner. And for the second part is that we have very wide tables with more than 1,000 columns. These tables are different from the normal tables. They have different time to live configurations for the columns because they have so many columns. So some of the columns are actually they don't want to retain them for like more than 1 day. And some of the columns they want to retain them for more than a month. So if you use a single say time to live for the whole table, that will retain a lot of unnecessary storages. So we derived our in-house strategy to expile these kind of wide tables, expile their columns. The third part is the storage tiering. So there are high priority businesses. They want to, they have the budget to store their data on the SSD device, say, in the first place when the data is still accessed very frequently, say, hot. So after that, when the data cools down, we rewrite those data from the SSD device onto an HDD storage device, saving some of the storages. Even after that, we can change the compression scheme of the storage. So at first, we're choosing maybe the gzip compression scheme, so because the data is accessed relatively frequently. But after that, when the data cools down, we can choose a more aggressive compression strategy like the ZSTD to further reduce the table storage. The second goal is lowering the computer cost. We know that with this many Iceberg tables on the storage device, we are actually generating a very large amount of small files on the storage cluster. If we query directly against these kind of small files, there will be opening cost, combining cost incurred, and also by accessing these kind of small files repeatedly, we will incur pressure onto the storage cluster. So by rewriting these kind of small files into a single file, we can save those costs. We already have a community version to do this quite well. On top of that, we observed that some of the costs occurred during the rewrite is not necessary. So typically when we rewrite a bunch of small files, we group them together to form a group. And first we open them one by one, right? We open the Parquet data file. Underneath that, we open the row group. And underneath that, we open the data page. We decompress data from those levels, and we get our records. We aggregate those records together to form a big data file. Then we compress them back into a Parquet file. That is a typical rewrite process. But among this process, some of the costs are actually not necessary, can be avoided. So say if one of the Parquet data files, it has a row group, say, that is already in good shape, say bigger than 4 megabytes, we don't actually have to open it, decompress it, and recompress it. We just have to open that row group and write it into the target data file. So underneath the row group in the data pages, we also have similar observations. So we can do similar things underneath that. We avoid to compress and decompress in these levels. By using this kind of storage strategy, we actually avoided quite a lot of the rewriting cost. So among all the optimization strategies, rewriting, expiring data file, removing orphan file, the rewrite actually costs most of the computation storage, cost of computation resource, like 90%, like more than 80% of the computation is spent on rewriting. So by developing this kind of in-house in-place packet rewrite, we actually avoided these kind of costs. So the third part of reducing the compute cost is by indexing the data. So we with the community version of the Iceberg, we already have decent data skipping by the column stats. So with column stats, we can already skip a good amount of the data, but we can do more. On top of that, we developed the file level index, like the Bloom filter index. So when before we opening the data file, we first check if the query could actually hit the data file by checking the Bloom filter index data. And using this way, we can further increase the amount of data that is skipped. So this further lowered our computation cost. The third goal is actually improve the data usability. So like I mentioned, our goal is to minimize the user configuration, user intervention. We automating those configurations for the user, the indexes, the options, etc. And on top of that, we actually tell user how things are working. We tell them how the optimization, what is the optimization status? Is it in progress? Is it failed? So that users have a good sense of regarding how their data are managed, if they do care for the knowledge data engineers. The solution of governing the hundreds of thousands of tables is to categorize tables into different tiers. So we've observed in our production data that the tables exhibit quite different rewrite patterns, and because of their business requirements, they actually require quite different optimization service level agreements. So at the right-hand side is actually a commit frequency histogram. So this is a histogram for the tables that with commits more than 100 times every day. So we can see that there are very frequent table write tables. So you can see that they have more than like 1,500 commits every day. So the large amounts of the tables actually occur here. So we have tables with more than 100 commits every day, 300 commits every day. So the below in diagram is the ones with the commits less than 100 times. We can see on this histogram, the tables are accumulated within the 1 times to 10 times interval. So with these observations, we can categorize tables into different categories. We categorize them into 3 categories. So the tables with service level agreements in hours, their writes occur every few minutes. For these kind of tables, they are usually very important. So optimization config is actually also could be anticipated from the user in a timely manner. We sit together with the user regarding how to make this table working the best way. The users are actually willing to spend time to tune these tables with us. So we also have a second of the tables that is optimized with service level agreements in days. So these tables with writes occur over several days. Users might configure these tables, but we don't anticipate that they might configure these tables, they might not. And the third part is the tables with less frequent writes, they commit only over days or several days. So we don't anticipate users to configure these tables at all. A solution to meeting the SLA is our platform. So we have a roughly sketched service like this. So our Iceberg applications running in the production, they all produces application events, and those application events are collected and put into one way into the message queue. So these commit event, like the commit events, it will go through the message queue and into our auto optimizer service. We will read those table commit events, and we will create optimization jobs for the corresponding table with those commit events. For the other way, it's an offline processing. We have scan events, so we can extract very detailed information from those scan events. So we aggregate them together into insights, into like how we configure those data clustering columns, things like that, etc. So we after we calculate these things offline, we put them into an OLTP database, a MySQL database. And when users ask us regarding how to configure those tables, we will provide these kind of information to them. Also, regarding these optimization jobs, we collect the status from these jobs, and we also provide these kind of job statuses to the user so that they know what data are optimized and what data are not, so that they can, when they care. So when managing the daily, weekly tables, the optimization is actually triggered by the commit events, like mentioned. So after accumulating a certain amount of table commits, we will launch an on-demand optimization job to optimize that table. When optimizing those hourly tables, those very, very important tables, we actually launch a stream job. The stream job will sit there, continuously polling the table metadata for information, for things that they could optimize. The optimization job is performed as a streaming job. So when the jobs fail, we monitor those failed status. If the failing could be rectified, we will rerun the job. Sometimes there are random errors in the production environment. So we will rerun those jobs a couple of times if they could success. But if the job still failed, there will be monitor and alerts sent back to the users, sent back to us. We will come in and fix those jobs. Lastly, like I mentioned, the user will have a UI regarding the details of the optimization. So there are several limitations within the code that prevents us from running this large of the Iceberg lake. So first is the lack of a delta rewrite. Lack of incremental rewrite. Well, currently, when the community version, when we want to rewrite only a portion of the table data, we have to pass in a data filter. So users have to have knowledge regarding the table schema, what partition are they on. They have to configure those kind of things, but users don't configure these things. We want a way to automatically filter a portion of the data using the data time, but we don't have a very good way to derive the data time from the partition data, from other information we have in the code. So we come up with a solution to address that. So the second limitation is regarding the huge amount of V2 tables with huge amount of data files and equality deletes, because the equality deletes could be referenced by multiple data files. So when we rewrite those tables with large amount of data files and the quality deletes. It could be the case that one of the quality delete will be opened by multiple data file readers, and the optimization job will be stuck when the readers are competing for reading the deleted files. This is a known issue in the community, and there are ongoing discussions for this. And the third limitation is the downlink deletes. So the delete files are only removed when we are doing the commit, but because when the commit interval is very short, and at that time we could do very expensive partition scans because it will slow down the commit. So we have an approximation regarding what delete file to remove, but the cases are that some of the data files could retain delete files in other partitions. So this is not what we wanted. So we are enhancing the course to address these limitations. So first, in terms of automatically incremental rewrite without user intervention, we approach the data time through the manifest data file modify time. We actually check the manifest modify time and data file modify time. We use that data file to filter out a portion of the data to rewrite. So using this way, we can do incremental rewrite for all of those 100,000 tables with no user intervention. So this approach works for most of the day plus service level agreement tables, but because it is an approximation, so it will include some of the recently modified manifests, some of the recently modified data files. So this typically works for most of the tables, but for some of the high priority, very highly write, highly frequently write data tables, it could be some times this approach is problematic. So the V2 tables, to solve the data files competing for joining the equality deletes, we derived a joining scheme for rewriting the V2 tables. We treat the data files, equality deletes, position deletes as data frames. When deriving what records to be removed, we join these data frames together and let the underlying engine like Spark decide actually the optimized execution path. So we ensure all delete files are opened only once. The data frames, we make use of all the underlying computing resources to rewrite these kind of V2 tables efficiently. And regarding the removing downlink deletes, there's already a agreed approach in the community. So we are actually adopting that in our implementation. So that solution is still under discussion, but we picked it down and using it in our production environment. We also, I will briefly skim through the index configurations, how we derive them. So we have Iceberg scan events collected from the applications. So say, for example, we have one of the events scanning TS, one of the events scanning ID and TS, the third scanning ID, the fourth scanning the data and the TS. So aggregating all these events, we have that we scan the TS column 3 times, ID twice, ID TS once. So from this aggregation, it seems that TS is actually a good candidate. So this is roughly how the data is generated, the configuration is generated. But there are a few details, like we will have to filter out the partition columns, filter out the low cardinality columns. So using this way, we generate the index suggestion to the user. So the future work is still 2 aspects: further reduce the computations, further reduce the storages. We want to enhance the core. We have developed in-house strategies to reduce the bin pack rewrites, right? But there are still sort, and there are still V2 table bin pack that cannot be applied using those strategies. But that still costs a lot of the rewrite computations. Regarding the storage, we want to automate how user to configure those time to live days. So these things are preferred to be automatically derived as well. So we want to optimize on that way. So the conclusions, we managed to optimize like 100,000 tables currently in production. We categorize them into different tiers to meet these different service level agreements. We enhanced the community version optimization call to meet these service level agreements. We derived the optimal optimization configs for these tables. Yeah, so that's basically what I have. Do you have any questions?
All right, Albert, thank you so much for that. I would now like to go ahead and open it up to questions from our audience. Please go ahead and use that little Q&A tab towards the right to go ahead and drop your questions in. Albert, I'll go ahead and read you some questions that did come in. So let's go and start off with the first one. How do you compact and how often? For example, do you compact at the end of each job run? Or is there an externally scheduled process to do the compaction across tables?
We actually don't. So the question is, let me actually repeat the question. So the question is, where do I do the compaction? Inside the right job or with the external like job, right? So
correct.
Yeah, so the approach we do is that we have a different job. We don't do it in the write process. So we have a different job. We launched that, like I said, that when we receive the table commit events, we launch a different Spark job that does the optimization. So in a different process. So that's not done in sync.
Okay. Thanks, Albert. The next question that we have is, can you share more about your indexing approach? Is it part of Iceberg or something external?
I think there's some ongoing discussion within the community as well. But currently, the index scheme we have is we have actually implemented the Bloom filter index scheme for data file. Like I briefly talked about it. So when visiting one of the data files, we first check in the Bloom filter to see whether data will hit this file. If the Bloom filter suggests that the data file will not be hit, then this data file will be skipped. And we also have the rolling bits index currently. So that's basically what we have at the moment.
Okay, great. Once again, folks, if you guys have any questions, please use the Q&A tab towards the right to drop your questions in. We've got about 10 more minutes here. So the next one is the storage tiering built in-house? I don't recall Iceberg having such a feature.
Like Ryan mentioned in his opening addressing, so Iceberg core provides very solid atomic functionalities we can use. So also in this feature, the storage tiering, that feature is the rewrite. So the so-called storage tiering is actually moving the data from one storage device to another storage device. So it's actually it actually could be achieved by rewriting the data files from one pass to another pass. So you can like using a little bit of configuration, you can using the rewrite job to achieve what is so-called the storage tiering.
Okay. Next question we have is, how do you handle parallel writes on a V2 table, especially concerning commit errors due to multiple writes?
That is actually a hard question because, So V2 tables are actually a little bit difficult to manage. That is why we have a very little actually amount of them in the production environment. So when different processes writing simultaneously into one Iceberg table, they will compete for the commit. So it's actually not that important regarding whether they are V1, V2. So even if they are V1, there are many writers competing for the commit. There will be conflicts, and there are limited things that we can do to optimize this. So the best strategies that I have at the moment is that we should control the concurrent rewrite number, say limited down to within 10, and we can increase. We have to make sure that they don't overlap, and we increase those commit failure retry number so that we can make them cooperate well together. Apart from that, so if they like overlap with each other with a large portion of data, so that will there's no good way to overcome that at the moment, as per my understanding.
Okay, great. Next question we have is, can you explain about Parquet in place updates and also row group updates?
So the question is regarding the Parquet row group in place rewrite, right? So I talked about it a little bit in the slide. So like I mentioned, some of the compression and the decompression regarding the row groups are not necessary. So if the row group is already in good shape, say it's already exceeding the rewriting threshold, say 4 megabytes, we don't have to decompress them and recompress them. We just read that row group in binary. Right? We don't decompress them. We write that out directly onto the target file.
Okay. We've roughly got about 5 or 6 more minutes here. All right. So the next question is, how do you do tiered storage with Iceberg? Albert, are you there?
I think I have mentioned that. Yes.
Okay. Did you hear the question?
Yes, but that is already answered. I think that is
Yeah.
That's already answered, right?
Yeah. All right. Let me go ahead and go to the next one here. Do you have any access controlling over Iceberg catalogs?
That is not that is actually not within my familiarity. So I will leave that question.
Okay. All right. Next question. Does Iceberg provide a REST service for interacting with Iceberg metadata?
For our practice, we actually didn't use much of the REST catalog, but that is actually, I think that is actually largely required for the, I don't know, like small businesses, because running a large Hive meta catalog requires people, requires certain amounts of work. But with the REST catalog in place, maybe the burden of maintaining this kind of catalog service is actually decreased. That is my understanding.
Okay. Another question just popped up here. How do you handle data retention? I'm not sure if you already covered this.
The data retention, yeah. So usually we have a default time to live for the data, say a week. That data that is older than that period will be removed automatically using the delete procedure. So at that time, the data is actually still within the metadata's whole, right? So we have the expiration metadata procedure, right? So that is also a request configuration. We have a default configuration for that, like 2 days. After 2 days, so the deleted data files will be released from the storage. And underneath the storage clusters, they have their recycle setups for the data. After the recycle expires, the data will be removed permanently.
Okay. Let me see if any other questions have come in. I'm not sure if you talked about this about AWS S3, but how do you control the number of output files and or their size in persisting layer? Example, AWS S3.
Yeah, so this is actually a very, say, fabricate. This is actually a very, I don't know how to say that. The target file size actually is a very good parameter to tune that. And this actually controls various aspects of the table, especially the querying access. So if your table is very, very large and the target file size actually usually should be large in order to skip more. So in order to have a say the small number of data files generated during the write process, you should have tuned the target file size and target row group size, and tuning these tables will be very useful especially useful for the large tables and increasing their querying performance.
Okay, maybe one or two more here. All right, so how do you handle concurrent writes for tables with high frequency writes and their corresponding compaction jobs?
Yeah, so previously there was a question regarding only the conflicts within the write jobs, right? So this is talking about the rewriting jobs. So I will just explain the rewriting job and the write job conflict. So usually there will not be a problem because the rewrite is not that frequent, and most importantly, the writing process doesn't generate conflict data with the rewrite process. So when the rewrite fails, it's not because there are overlaps between their write within the write process. It's usually because it's not holding the lock of the current commit. So you try a few times, it will actually solve the problem. And for those very high frequently write tables, the rewriting frequency is actually not that high. It's actually in hours, like I mentioned. So there will not be like rewrite in minutes, things like that. So this is actually fine.
Okay, great. That's all the time we have for all the questions. Thank you for joining us. Thank you, Albert, once again for a great session.